Okay, good afternoon, everybody. For those of you who don't know me, I'm Richard Szabo, and I'm the chair of COST Action MP1405 Quantum Structure of Spacetime. So I'm not going to be saying much here. I just want to give a little introduction to this event. This was a 4-year project, and we are now coming towards the end of that 4-year project. So this is the end, the final main conference. Over the 4 years, the main remit of this action has been to explore the notion of quantum structure of space-time in its broadest sense. So this has started, it has its seeds in a group of us who were working on non-commutative geometry and trying to understand what that means in terms of quantum space-time structure, but the action itself is much broader. It involves both aspects from theoretical physics, from mathematical physics, indeed in pure mathematics. A big remit of this action is using pure mathematics, right to the other spectrum in experimental physics, and also, as we heard this morning, in the philosophy. So you've seen this week a very broad spectrum of things that really reflects what this action has been about for 4 years, and since this is the last workshop of the action, and the action will finish very soon, we thought it was only appropriate that we should have some kind of an open discussion session with some very distinguished panelists, exploring some of the various ideas that people from different areas have about the notion of quantum spacetime. Okay, so I hope you'll enjoy this session. I'm looking forward to some very lively discussion and debate on some issues, and with that I'll pass this over to the convener of this round table, Professor Fedele Lizzi.
Okay, thank you, Richard. Thank you, everyone. Okay, let me briefly introduce you the member of the panel, and starting from the left, my left, is Petro Horava. And he's at the same time coming from the most far away because he's coming from California, but he's also semi-local because he graduated in Prague. And as a student, he discovered independently from Polchinski and collaborators deep brains, but he's also famous for Horava-Witten theory on domain walls, and more recently, Horava-Lifshitz model on renormalization and change of dimension at short distances. In fact, we heard a talk recently. Then near me here is Mary Sakellariadou. I usually pronounce it well, but she's a professor at King's College London and graduated at Tufts University with Vilenkin, and has been active most in cosmology, and lately in various versions of non-commutative geometry, in particular the gravitational and cosmological aspects of the Shamseddin-Kohn spectral action. And in the action, she's a member of the action, and she's the working group 5 leader. On my right is Roger Penrose, who is Penrose. Presenting him is, I don't have much time. There is a list of 31 items on Wikipedia connected with him, and he has many awards, including the one from the Queen, of course, and the Heinemann Prize and the Dirac Medal, and many more. For what we are concerned for this action, I would certainly mention twistor, black holes, and non-self-repeating tiles, which is one of the examples of the non-commutative space, or rather the quotient of the plane by these tiles, is in Alain Cohn's book, and with beautiful pictures. Then there is Professor Sergio Ferrara. Is from Rome, where he graduated with Marco Toller, and has been for many years at the theoretical division at CERN. And for us, for many of us, is synonymous, his name, with supergravity. He introduced it with Van Nieuwenhuizen and Friedman, but also supersymmetric H theories and lots of super other things. He has also several awards. The Heinemann Prize, both of you have it, and a different Dirac medal, the one of ICTP. And further to my right, so to your left, is Harald Grosse, is coming from closer yet, because he's from Vienna. He graduated there with Hans Stirring, and is one of the... Walter Thierry, I'm sorry. The Thierry model, not the Lenz Thierry one, I'm sorry. And is one of the most senior people in the non-commutative geometry. First paper I checked is 92, so I don't know between him and Ali Shamseddin, we see here also, who is the first, but they're certainly the doyens of our group, and most important in field theory on non-commutative spaces, and the most important things with this work with Reimal Vulkaner most recently. So once I introduced everyone, I will start with a question, and we will have a few rounds of questions, and then perhaps, but certainly I will open the discussion to the floor. So the first question which I wanted to ask, I want to know the opinion of the panelists, is the following. Several physical theories are geometrical theory, classical mechanics, general relativity, and several others. And in classical mechanics, we know that when we go at a certain scale, which is a scale of h bar, the geometry changes drastically, and we have this scale. This is the dimension of the area of phase space, and we have a different kind of theory. Now, the question is that, will the classical geometry of gravity survive up to the Planck scale? And I think we can start from some of you, of course, I know the answer. I know what you think, but please.
Okay, I think the answers might be very dependent on whom you ask. I don't even know if I have a uniform answer, but certainly the things that I have been working on are based on the premise that the things that we are willing to give up do not include smooth geometry. I think it might be too early, or it might be wise to actually try and see what happens if we take both the a priori existence of the quantum and the laws of quantum mechanics and the existence of some form of smooth geometry seriously. And as far as I'm concerned, the smooth spacetime might survive all the way to the Planck scale, for all we know, and it might just be the structures on that smooth manifold that might be modified. But there are days when I wake up and I think it's the other way around. So I think that, to me, indicates that we are really living in an exciting era when answers to these questions will be ultimately driven by comparison to experiment. And we have lots of new data coming in, both observationally in cosmology and in particle physics. So we are finally confronting whatever preconceptions we might have with the real world. And I think that should make all of us excited about finding the right answers.
Yeah, I think that the geometry as we know it is going to change. And now the way is how. So if we want to discuss, to describe gravity and quantum mechanics at the same token, then they should be the same language. So in the case of gravity, which means instead of taking points in a manifold, we're going to take the algebra of the coordinate functions. So if you take quantum mechanics, then there is an intrinsic kind of non-commutativity there, because we know that we have non-commuting between the position and the momentum, so it's going to be kind of non-commutative algebra. So then you have to, I mean, in a classical space, we use any kind of geometric information we have, like phase space. And of course, this cannot be automatically encoded in the quantum approach, which means that when you take the quantum algebra of your observables, it's going to be a sub-algebra. So you lose some information, which means that you see this kind of geometry, if you want to call it, to be like a fuzzy space, whatever that is. Now, certainly, you can build theories like that, and you can test them by trying to find the semi-classical limit of the theory and see whether this can be tested with data we have. And then arises the big question: what do you mean by semi-classicality? How do you define it? And the results might depend on that. So, certainly, is an area which is very promising, and there are different approaches that one can follow. But I believe that the geometry, the notion of geometry we have in a classical space should not hold in a quantum kind of system.
Sir Roger.
Well, perhaps I could make several comments where I have somewhat unconventional views about these things. First of all, the question of quantum gravity. I like to look at that there are really two ends to this subject. One is how quantum mechanics would affect the theory of gravity, and the other is how gravitation might affect the theory of quantum mechanics. And when it comes to experimental tests, the idea of testing, the nature of geometry at the Planck scale, we're nowhere close. Whereas we're looking at the other side, how gravity might affect the structure of quantum mechanics, I think we're very close, and we may see deviations from current quantum theory due to gravity. But I think what we're talking about here is not that end of things. I just wanted to make my position clear that I think the two subjects will affect each other, but in ways which are much more immediate to experiment in the other direction, not from what I think the question is here concerned with, namely the small structure of space-time, which would be presumably what one is probing when you look at very high energy events. Now then I also have a somewhat strange comment to make, I think, because later on, well, tomorrow evening or whenever it is, I'm giving a talk on this cosmological scheme I have, which rather goes against what I would have thought previously, namely that a role for quantum gravity would be found in the nature of the Big Bang. And this always had been one of the reasons for looking at quantum gravity and seeing how its effects might manifest themselves in the universe we see, and the Big Bang would be a good laboratory, or perhaps the only one, where you see effects of quantum gravity on observational scales. But the point of view which I'm plugging now, and for which there does seem to be some rather remarkable evidence to support it, and I'd like to see arguments both directions when these are brought forward. But what it seems to suggest is you have to treat the Big Bang as being really very smooth manifold. And you don't see complicated regularities, wormholes, or whatever it might be, or discrete structures, which you might expect to see on the very small scale. Now, the thing is, this is looking at things on a conformal scale. So you maybe have a different picture. And the picture I have here, really, is that if you have large curvatures, you see the argument was, if you get near a singularity, then space-time goes crazy, and who knows what goes on. It would be some quantum effects which start taking over. But what does one mean by the curvature being large? Well, if it's the Weyl curvature, then that's the conformal curvature, and the argument here is that in the Big Bang, it's very, very small. And so therefore, even though one might expect to see huge changes in the structure of space-time when we're probing large Weyl curvature, that's not being probed by the Big Bang. So I'm not really putting forward a position with regard to quantum gravity. I'm just saying that it doesn't seem to be what's relevant in the Big Bang, which is a somewhat going against my own views, but the thing that I think now is probably more likely to be true. On the other hand, when we are looking at situations where you're looking at the very small structure and where it's not just simply looking at the Big Bang, I think that the thing I talked about earlier today, where I didn't really get to this point because there were too many other things to say, there were two symplectic forms, which I mentioned near the end of the talk. One of them had to do with general manifolds, which doesn't really probe small or large because it's purely conformal, and that was one of the symplectic forms. The other symplectic form comes in when you're looking at gravitational effects. And the argument here would be that you do have, although it wasn't what I was using in the talk, except I think it was on the last transparency, that you could have a commutator relationship which is not the one I had been playing with before, which seems to be just to do with classical geometry and conformal geometry at that. But when you're looking at Einstein's field equations and you're looking at the metric, then you bring in this other form, and it would seem that when you have to consider both forms, well, they both give you commutator. You think of them, or maybe the Poisson bracket associated with that, and that gives you a commutator. And so you do have a commutator from that other form. I haven't explored that, but this would be my suggestion. Look at that and see what comes out of it, and that might give you a good idea. Maybe something combinatorial is rather than continuous. It's quite possible. That might well give you some insights into what's going on in the small scale. I don't know what it is, because I haven't explored that, but I'm just proposing that as a route to follow, which might tell us something about the very small scale structure of space-time.
Okay. Sergio? Oh, yeah.
Break symmetry.
Professor Penrose na topologically non-trivial.
Doesn't work.
We do that.
Well, my main work has been in the past to consider gravity in the framework of supersymmetry, and I want just to make 3 or 4 observations which may explain why supersymmetry has to do with the theory of quantum gravity. Well, first of all, the nice thing about supersymmetry is that it works with an unconventional algebraic structure, which are the superalgebras instead of ordinary algebras, like, for instance, Professor Penrose was studying twistor, but with standard symmetries. In some sense, supersymmetry is a theory of, twistor, but not with an algebraic structure, but with a superalgebraic structure. But the main ingredient is still twistor in string theory, because fermions play a fundamental role in a theory which unify bosons and fermions. The nice thing, however, about supersymmetry is the local extension, because in that case you must have an extension of diffeomorphism, which you can call super diffeomorphism. And the interesting fact is that you discover, as Wess and Zumino proved long ago, that the naive super-Riemannian geometry is actually not the underlying geometry in supergravity, but is a much more complicated geometry, where actually the notion of supertorsion plays an important role. The other 2 aspects, which may have to do with the quantum structure of gravity, is the fact that supersymmetric theories of gravity give a bound in the dimension of space-time, as much as the same Elena Castellani was telling this morning about the bound in the dimension in string theory. This bound in the dimension is actually d equal 11, a result which was obtained in the early stage of supersymmetry by Werner Nahm. And the interesting fact is that, so there are, in some sense, there is a bound in this dimension of space-time, while in ordinary gravity you can have an arbitrary dimension of space-time, as Roger Penrose was pointing out this morning. And of course, the highest dimensional theory is M theory, a theory which is not still shown to be consistent like string theory, but which is believed to be the theory which unifies everything. The crucial ingredient in M theory and all theories of gravities, which are supersymmetric, is the existence of extended objects. This is a very important notion, because extended objects introduce a fundamental scale in theories of gravity, and this fundamental scale leads to a modification of the Heisenberg indetermination principle, because you get a correction due to the extension due to the dimension of the extended object. So a modification of the indetermination principle is actually a pure quantum phenomenon, because it's a correction to a standard quantum theory, to a theory which has more structure than ordinary quantum mechanics. So you would call it super quantum mechanics. So I think these issues can be debated because if one really believes in string theory or supergravity or supersymmetric theories, you would expect also to be a theory which could be falsified, not at the Planck scale, but at some much lower scale. And the existence of supersymmetry was actually one of the major goals to construct the LHC and the still LHC accelerator there is some hope that in the future this accelerator will discover new particles, either they are supersymmetric or not.
Yeah, it's okay. Thanks. It works. Yeah. Okay. Thank you. Okay. So I feel, I mean, these two pillars on which we have the modern physics lying, I mean, GR and quantum field theory, relativistic quantum field theory, are very powerful, but both show in a way the limits. That impresses me always. I mean, you can think also classical electrodynamics, for instance, and the models we are building show their limits. In GR, of course, we know all, I mean, the information paradox or black hole physics or early universe questions and so on. But in quantum field theory, which I'm much closer, I was always puzzled because of the singularities. Not those which can be hidden in the renormalization scheme, but the additional singularities, like the convergence of an expansion, for instance, renormalons, ghosts, Landau ghost, it was mentioned in lectures, and so on. So there are many singularities around which we should cure. Now, of course, it's impressive if we have a quantity which can be evaluated up to 10 digits, like G-2. But as I said, I mean, it should be UV complete. But if you say, okay, it's QED is part of the standard model, then in the infrared we have exactly the same problem with QCD, so to say. So, to my opinion, it shows the limits of the artillery which it produces, and we should take it very seriously. Now, to my opinion, to answer Fidele's question, I think both have to be modified, and they are modified already. If you think of loop quantum gravity of the one side, on the other side strings, well, as we heard. So both space-times will be modified, especially because I'm so eager to build so to say, an existing well-defined UV complete and IR complete model. I was happy in the late 80s to learn about non-commutative geometry by Alain Kohn. I mean, at least I tried. Also, it starts with KK theory. It was a bit ugly to start with, but then we saw certain parts which we can use, and we regularized the quantum field theory in an unexpected way. I mean, as we heard several times, with a fuzzy space, respecting symmetries, which every commutative space, if you go to a lattice, will break the symmetries. So these were unexpected things, and it was a beautiful time, especially I liked it, and we have been able to publish. But next came the question of renormalization. I mean, can we cure the problems of quantum field theory? And, well, I will give a lecture tomorrow. To my opinion, yes. In a certain sense, we cure it, but it's a long way to go. So I would personally say to young people always, they should spend much more time. They shouldn't immediately ask for supersymmetry next week at LHC. It takes a lot of time. And so our project also of constructing really an interacting four-dimensional quantum fields here. In Euclidean space-time, it's probably sooner or later finished, but in Minkowski space-time or Lorentzian metric space-time, it's completely open, to my opinion. Thanks.
Let me take up one point that has been touched by Pat, but then has been also, and is the smooth structure at the Planck scale. So if he said that at least half of the days you were not willing to give up on the smooth structure. There is another structure which I may add, which is the Lorentz structure, the Lorentz symmetry. And so how willing you are to defend this up to the extreme consequences?
Okay. That's a good question. I would like to start by mentioning that we already know, at least mathematically, a very consistent theory of quantum gravity, which is string theory. And we can, whether or not we think that's the ultimate answer to questions of quantum gravity, we can take some basic lessons. For example, the fact that in many ways the space-time geometry in string theory may be viewed as emergent. And it's very difficult for me to think of an emergent structure giving rise to a space-time where the Lorentz symmetry is also not emergent. Because if it's not built in, I mean, if the space-time is not fundamental, then how should Lorentz symmetry be fundamental? Maybe that's one lesson we can take from string theory. But I think in more generality, it's not just the question of whether you want to keep the smooth structure of space-time or some other, such as Lorentz invariance of space-time, but the question that we should be asking is, what do we think gravity is a theory of? Is it a theory of the space-time, or is it a theory of the space-time geometry represented by some metric structure? Certainly at long distances, it's primarily a theory of the metric geometry on space-time, and not necessarily saying anything about the underlying differentiable structure of the geometry. So you can imagine decoupling those two and treating them as separate structures of different level of fundamental nature or importance. So I can imagine treating gravity as just another many-body system, which just happens to be effectively described at low energies by a metric field on a smooth space-time without giving up the underlying smooth space-time structure with its own causality, which is pre-metric. You don't need the metric structure on space-time in order to have causality and other features that are so important in quantum mechanics. For example, in quantum mechanics, I'm a strong believer in what also string theory is teaching us, that quantum mechanics somehow appears to be an absolute structure, which we don't have a clue how to embed into some bigger framework. It's something that looks unique, and it's not an effective approximation to something deeper as far as we can tell. So I'm always taking the principles of quantum mechanics very seriously, including unitarity and causality, and looking at geometry and topology as secondary issues that may be modified more easily. So I guess the question is whether we think that the principles of quantum mechanics are the things that we need to keep absolutely because we don't have a good way of embedding it into a bigger framework, or whether we think that the geometry is absolute. And I think so far everything seems to indicate that the geometry is approximate, but which parts of the geometry, is it the differentiable structure or the metric structure or the causal structure, which ones are going to be modified? That's an open question to me.
Sure.
Sure, you take one of the microphones.
Just what I was... you don't think that, in some sense, the inclusion of extended object gives automatically a modification of quantum mechanics? I mean, the fact that the theory contains extended object, that in some sense should be treated in an equal footing with the metric.
I don't see it as a modification of the laws of quantum mechanics. No, I see it as a modification of the geometry of space-time and the way we organize our thinking about what is a part of the geometry and what is a part of the matter system living on top of the arena of the space-time. So in string theory, everybody is unified into being a string excitation or maybe a brane excitation, maybe living on an extended object or being an excitation of an extended object, but that doesn't change the fact that we rely on the basic principles, I would almost say, of the Copenhagen interpretation of quantum mechanics, because we don't have a clue, and we are not really even trying to change it to something more generic. So I think quantum mechanics has survived so far, as far as I can tell, in string theory without any modifications.
But you're talking about quantum mechanics in the world sheet or quantum mechanics in space-time?
Well, I would say quantum mechanics is controlled by some H bar. And I need an interpretation for it, and I'm not seeing any framework which would treat our conventional way of treating quantum mechanics as an approximation to something bigger, which I feel like we should be nervous to have a theory which, for the first time in the history of science, is not an effective approximation to something deeper. We don't have a way of embedding quantum mechanics into some broader theory. On the other hand, general relativity is easily embeddable into something where there are higher curvature corrections and so on, but quantum mechanics, in my view...
Quantum mechanics means H bar. But it's
well,
with the extended object. You have alpha prime and the
oh, sure,
which play
right.
a similar role. So this is why I was thinking about modification of quantum mechanics.
In the long run, I would be very open to it, but I just practically don't know how to do it now. So I would say, for now, we don't... In string theory, it's my conviction that we don't know how to abandon quantum mechanics or embed it into something bigger. It basically asks us to be imposed as a set of axioms, and within that set of axioms we can modify geometry very successfully, and we can introduce other scale parameters like alpha prime very successfully, but we are not changing the basic interpretation, probabilistic interpretation of the quantum mechanics setup as it has been around for more than 100 years.
Okay, let me give the mic to Roger.
Yeah. I'm sort of surprised, perhaps a bit shocked, by the idea that quantum mechanics, just because we don't have a better theory at the moment, which I agree with, doesn't answer the question of why we need a better theory. And I think we certainly need a better theory because quantum theory as it exists currently is self-inconsistent. I mean, it has different procedures. You have the evolution of the quantum state, the unitary evolution, and you have the measurement process. And the measurement process, as we currently use it, certainly, blatantly, is a contradiction with unitarity. Now, of course, some people would take this, well, we've got to go into the many worlds view or something like that, but of course that has its own problems. But as theory of the world that we see about us and how it behaves, it's not consistent with unitary evolution, because the measurement process violates unitary. So why don't we say, okay, I agree we don't have a better theory, but to say that means we shouldn't look for one or something, or at some people level, there shouldn't be a better theory. You see, I rather argue the opposite way. So okay, we have singularities in general relativity, and we have this problem, we also have divergences of quantum theory, quantum field theory. But those are not sort of, I mean, in general relativity, you get, under extreme circumstances, you get singularities. But you don't need to, if you're just considering how the universe is not close to a black hole or something behaves, or you're close to one as long as you're not close to the singularity. The theory has no reason why we should change it. Whereas quantum mechanics does have a good reason why we should change it, namely that the way we use it is a self-contradictory procedure. Okay, the Copenhagen interpretation gives you a way of living with it, but it doesn't answer why you do something different to your measuring device from what you do to the thing to be measured. I don't know. You can answer.
Oh, well, yes.
Okay, so
then I would like to hear also the other people.
I totally agree with Roger that we should be looking for something beyond quantum mechanics. I'm just observing that string theory, being a very successful example of something that has worked and taught us a lot about possible mathematical resolutions of various puzzles of quantum gravity, is not touching quantum mechanics at all and keeping basically all the problems that Roger mentioned intact, and at the same time revolutionizing completely our understanding of space-time. So that seems, in retrospect, to have been the easier one of the two challenges, and the challenge that awaits us is to see if quantum mechanics can indeed be embedded into something bigger. I think, again, to stress one more time that quantum mechanics seems to me to be the only known example in the history of natural sciences where we have an absolute theory which we cannot possibly treat as an approximation to something bigger. And we should be nervous because it has never been the case that any theory would have absolute validity. It's always an approximation where the corrections are waiting to be discovered. They're just around the corner. So, and with general relativity, I would slightly disagree with Roger on whether or not it can only be or should be modified at very extreme situations, because I believe if you treat quantum gravity in the effective field theory approach, which is a very legitimate, very meaningful point of view, which is, I think, shared by many practically minded people dealing with gravitational physics, experimentally, observationally, and theoretically, then all we know about quantum gravity and effective field theory suggests that quantum gravity actually breaks down at the energy scale of less than an electron volt, because we don't know how to answer the cosmological constant problem. And that, to me, is a big issue, which is asking for some serious modification of general relativity as we understand it when it's combined with quantum mechanics, and much earlier than we reach some singularity structure or horizons of black holes.
Yeah, something very, very brief. I mean, I agree and disagree with things that were said before. So probably one can see it either you have to quantize gravity or to gravitize quantum mechanics. And usually we just go to the way to quantize gravity. Now, certainly, it is this pathology of GR, as we know it. It is like you need higher order expansion, so you have higher other terms that we don't consider. And of course, quantum mechanics doesn't have this kind of pathology. But certainly, I believe we need another bigger theory, which probably none of us has, which is go beyond both of them. And probably so far we have been focusing in quantizing gravity, which is has been so far a bit unsuccessful. I mean, successful or unsuccessful, depending on whom you ask. But I believe we need to give up many of the things that in the limit of quantum mechanics and the limit of GR are valid, but at the higher limit, this assumption should not be there.
Fidele's question was whether smooth geometry will go up to the end, so up to zero. Well, I personally, of course, have the opinion that there will be a kind of phase transition to a kind of non-commutative structure, to a lattice, so to say. But of course, nobody can sort of prove it. Actually, maybe an interesting remark, in history, the founders of quantum physics were worried about exactly these questions in the 30s. Schrödinger wrote an article über die Unanwendbarkeit der Geometrie in kleinen Distanzen, on the inapplicability of geometry at tiny distances. He meant Riemannian geometry, quite interesting, because no formula at all. And Heisenberg was very much worried from the 30s up to 38 or so. He always, especially, I mean, it was published quite late on introducing a kind of lattice cutoff, a three-dimensional lattice, the Heisenberg Gitter, so to say. At that time, actually, they didn't exchange emails, they wrote letters. And in letters, already in 1930, he wrote to Ehrenfest and Bohr that he worries about X and Y and Z, why they are not quantized. But he doesn't know how to do it. So my excuse is actually nowadays we have Euclidean quantum fields, and that's much easier, and therefore we can do something. And we have Alan Kahn's non-commutative geometry and mix it together, so to say. With Lorentzian geometry, you have always a unitarity problem around. Russians, actually, Kardashevsky and Mir Kasimov, they tried in the 60s, but they had always consistency problems with unitarity. So I personally always feel consistency should be the way to go ahead, in the sense of the tiny distance, the tiny points where our models fail should point to the new direction, so to say. And we have to cure the singularities which are around on both sides, to my opinion.
Make a comment to Sergio and know his opinion. He's talking of extended objects. Now, you really need extended objects, or is sufficient to have a scale which will change things? Because an extended object means that there is something big, like a string, in an ordinary space-time, sitting there. Having instead a scale, like h bar for quantum space-time, means that you have to really change your, you cannot embed something in space-time. You don't have space-time anymore. So in your view, you need, is the extended object necessary, or a scale would be sufficient?
Well, it looks to me that you need, because of space-time supersymmetry.
Okay.
These theories of
the
gravity, for instance, M theory, of which Horava gave a substantial contribution, is a theory, is not a theory of string, for instance, is a theory of 2 branes and 5 branes, and the metric. And you need this object to make M theory consistent. So this object must exist in the at least in the Lagrangian formulation of the theory. Like in gravity, you need a metric if you want to make a Lagrangian formulation. In these theories, if you want to make a Lagrangian formulation, there are gauge fields of higher rank which couple to extended object. And so these extended objects are similar to the case of 4 dimension to black holes.
Okay.
Black holes is a 0-dimensional extended object. But the black hole, if you go higher if you have supersymmetry, are particular class of objects which are not only black holes, but you have black strings, black branes, and so on. And you need this to make the theory consistent, at least if you believe in this kind of theories.
Okay, so, but you start already from a theory of extended objects.
Yes, exactly. Yes.
Can I ask you something? Since you talk about supersymmetry, and supersymmetry so far at LHC has not been found, what is your prediction for, I mean, at which energy scale do you think that probably we cannot keep looking forever? So can you make kind of guess or at which energy scale, if ever, like an LHC, a new LHC can find supersymmetry?
Well,
that would be the experimental test.
It's very difficult to predict because the problem of supersymmetry is opposite to the problem that Roger Penrose was mentioning. Superstrings and supersymmetry theories live naturally in higher dimension. And to study the 4-dimensional world, you have to make a compactification. This compactification, at the beginning, was thought to be almost unique. Now today, in fact, we know that there is a landscape of solutions. And so the question of answering your question is you must have a study of the landscape and to see if in this landscape of solution there are favorable solutions which are at the energy scale that we look today.
Yeah, I mean, to my mind, to quantize gravity is something that we needed because we cannot explain black holes, we cannot explain Big Bang so much. But supersymmetry is something that we may be biased. We just want to have supersymmetry. We could live without it, no? So would you be ready to accept that there is no supersymmetry if we don't find it up to some scale? Or?
Well, supersymmetry regretfully plays a crucial role also if it is not said in string theory, because string theory are consistent only if they have space-time supersymmetric. So in some sense, space-time supersymmetry is demanded if you have superstring theory, and superstring theory is the only theory of quantum gravity we know today. So you can make this, but asking your question has to do with the study of the landscape in string theory, which is a very complicated problem. It's a statistical problem.
But if I try to be provocative, the fact that supersymmetry is needed in string theory is not a proof of existence or necessity of supersymmetry.
Well, if you believe that it's important to have a model of quantum gravity, as far as I know, superstring theory is the only model, you like or not, is the only model of quantum gravity which has not an internal inconsistency.
There will be many people in this audience which might have a different opinion. I'm not trying to say that it's correct or not.
This is why I'm giving my opinion.
Oh, great. Then you will be open to the floor. Okay, fine.
I don't think we have a very problem. That's
Yeah, that goes to my next question, which I had written here. So you are kidding, so I take back the mic. And the question that, as I have written, and do we know, how do we know that we are a theory of quantum gravity? Of course, one answer would be because there is an experiment. But then we have today morning the talk of David about non-empirical validation material. And I think that once you read the article of Einstein, people knew that they had an answer to the problem of ether. So, if we have the theory of quantum gravity, how do we know? Or do we think that there can be something coming from experiments in the near future? Because there is not only LHC, but there are also gravitational waves, and then they are exploring the physics of black holes. So the question is that how do we know that we got the right one? And I think probably we start from the other side this time, just to give people opportunity to the left and right.
So the question is, how do we know that we have the correct
theory of
quantum gravity?
Yes, no, there will be a moment in which someone we declare the prize. We declare, okay, we did it.
Since
we'll understand.
We don't know what it is. We cannot make only suggestions. And of course, I mean, the best is to have experiments or indirect observations, so to say. But I have something much simpler, actually, which is funny for me, which is superconductivity. In superconductivity, you have various layers of explanations. The simplest one is phenomenologically London equations. So you have one current and London equation. That's phenomenology. Then you have a Lambda input explanation, which is a kind of effective field model. One loop corrections, but to what? And then people found out to BCS model. And BCS model is super, it's simple, but it solves nothing. It cannot explain anything, people tell me. You cannot evaluate any gap directly or any transition temperature and so on. But it has a correct features. It has a Cooper pair formation and so on. So it has a correct transition mechanism, so to say, built in. And therefore people are saying, finished. To really describe material transitions, they have to go to Heriot-Watt models, it's called. But anyway, then it's becoming phenomenology, in my opinion. Now, something similar might happen here, because it's so tricky and complicated. Certain features should give us a kind of direction, and that can be, I don't know, in BZ 2, or BZ 2 failed, but BZ 3 or 4, or some signals which we didn't expect, but it was observed later on, so to say, that's what can be hoped for.
You want to say something?
No, the only thing I want to say is that you ask something more. You say which theory of quantum mechanics is the correct one. Here the problem is not which theory, because we don't have a variety of theories.
Okay.
The only thing in favor of things is that it gives a model for quantum gravity. But do you not? I agree with people who are against string theory, but people who are against string theory should provide another model which substitutes string theory. And I don't see this model. I know loop quantum gravity, which is related, but these theories are very difficult to formulate and to get results. But do you know any model of quantum gravity different from string theory?
The way that's phrased, I'm uncomfortable, because it's suggesting that string theory is a quantum theory of quantum gravity without. Let's address your question. No, you didn't say that. No.
Okay.
No, but other people here are saying it, and I'm worried about that. because I don't think it really addresses the problems in general covariance, all sorts of issues that are problems that we worry about in general relativity don't seem to be addressed. It just addresses some other aspects of it. Let me not talk about that, because I don't think that was the question here. The question was, okay, we're not looking for experiments because they're way off the picture, that's the idea, but do we have some theoretical reason or something to believe that this thing is correct? Actually, my viewpoint on that is it's got to be something which addresses both ends of the problem. If it's really going to be a coherent theoretical scheme, it has to address both the level at which quantum mechanics dominates gravity and at which gravity dominates quantum mechanics. And the theory has to cover both ends. So it would have to agree, in my view, with the measurement issue, which, in my view, is an issue where gravity is starting to be the dominant thing. So I think we can't be here at the same time because it has a significant gravitational field, and treating that according to the rules of quantum mechanics leads us to inconsistencies. And so basically the inconsistency is between the principle of equivalence, which is fundamental to general relativity, and the principle of superposition, which is fundamental to quantum mechanics. And you see there's a huge tension between those two things. So I would say that if you're going to judge the theory on its internal structure, and not experiments, then that internal structure has to resolve this issue at both ends, not just when you're looking at tiny, Planck scale phenomena, but also when you're looking at large scale phenomena, where somehow the classical world seems to dominate over quantum phenomena. And this is not something which is internally part of quantum mechanics. We've got to go beyond quantum mechanics to see why measurements can be real things which look like classical objects. And there's a huge problem there. And theory to be internally coherent to the degree which I believe it must be, and maybe without experiments, you would say, this is pretty interesting theory, because it copes with all scales, then okay, that would be a good piece of evidence, even without experiments. But I don't see we're anywhere close to that.
Yeah, let me start by saying that I have nothing against string theory. As far as I'm concerned, I have been testing different candidates of quantum gravity. One of them is string theory. But my opinion is that, unfortunately, I have to say that as far as I'm concerned, we have non-successful theory of quantum gravity. We have different models. All of them have positive and negative aspects. Now, a theory to be quantum gravity acceptable, then, of course, as was said before, it has to solve the ultraviolet and the infrared region with the same token, and that's not the case so far. Now, the question is, how do you test the theory? First of all, the theory has to be self-consistent. But this does not mean, because it is self-consistent and mathematically it's correct and beautiful and nice, that has something to do with the space in which we live, that is natural or not. So there you have to test the theory. And there where, to my mind, the difficult thing appears. Because in order to test the quantum gravity, we cannot do it. We take some kind of simplifications, and then by the end of the day, what we test is the simplified version of the full theory. So we cannot say that much whether the full theory is correct or not. So we have various proposals now. I believe that, the string theory has its merits and its negative things. For instance, this idea of the landscape, to my mind, is a very big pathology of the theory. On approaches of discretizing space-time, like LQC, where I have worked as well, I find the big negative aspect is how do you put the matter content of your theory, and so far it's put by hand, we have to accept it. So there are plus and cons everywhere. There is a problem to my mind here, is that each group works in his or her own direction. We should try somehow to merge the approaches and learn from each other's kind of approach if we want to go ahead. But up to now, I don't believe that we have any kind of theory which we can say that is the quantum gravity theory. It has to tick all boxes, and we're not there yet.
Okay, I feel like I have to defend Sergio's point of view a little bit, because I think string theory has really lived up to a very high standard. And the question is, what do we wish to accomplish? Do we want to solve all the open problems? Ideally, yes, but we probably have to move in stages. So I would say string theory doesn't necessarily automatically solve all the open questions, but you should ask yourself if you were able to find a theory of quantum gravity which would be at least as good as quantum electrodynamics or the theory of the standard model for elementary particles, would you be happy with that, at least as a working example? And I think for the time being, without being able to address some of the deep questions that Roger was mentioning in the fundamental principles of quantum mechanics, we would be happy if we had a theory of quantum gravity which is at least as good as quantum electrodynamics. And I think string theory is that, at least mathematically on paper, because it allows you to calculate graviton-graviton scattering consistently. It has all kinds of beautiful properties that make you think that this theory is in some technical sense UV complete, and how much more you want to ask at the first stage. So in that sense, I would like to see any other proposal for a quantum theory of gravity to live up to that same standard and provide a calculation for at least simple processes, including gravitons. And I don't see too many such theories. So I think on that note, I would like to defend string theory and Sergio's point of view.
I think another important aspect of string theory,
Take a microphone.
which come...
There must be a mic. Okay, no.
Another important aspect of string theory, which is the notion of duality. And in string theory, there are two notions, which actually is originally taken from the standard electric-magnetic duality of Maxwell-Einstein system. If you have a Reisner-Nordstrom black hole, which is dionic, you find that the entropy is invariant under the exchange of electric charge and a magnetic charge. And that is what is called duality, electric-magnetic duality. In string theory, there are generalization of electric-magnetic dualities in view of the presence of the extended objects. And in fact, essentially what happens in these theories is that there are different formulations of the theories where you use different variables. And what happens is that what is a classical process is one theory. In the duality-related process, it becomes quantum process. So really, it doesn't make much sense to talk about quantum versus classical if you don't choose first the right number of the right variables. And this, I think, is a very important aspect of of theories with extended objects, which is this duality between different formulations of the same theory, using different variables depending on the regime that you are considering the theory.
Okay, having geared up to a healthy discussion, I think it's the moment to increase it even more by opening the floor to comments and questions to the panelists from the public. In particular, I want to, since the action was about non-commutative geometry, I don't know if Ali Shamsuddin, who is one of the doyens of non-commutative geometry, has some comments to make.
Well, thank you. One point, actually, which was not addressed in this discussion is that concentrating only on quantum gravity and ignoring the other forces in nature, because we know actually the other forces are there, and traditionally it has been, people were looking for a unified theory of all interactions, including gravity. So, it doesn't make sense simply to look at gravity isolated from the other particles, because in the end, they have all come at the same time. And so in this way, actually, even if one looks at string theory, doesn't really give an explanation, for example, why the standard model, why actually nature did choose the standard model, why, for example, supersymmetry has not been seen up to now. So this type of questions, has been answered in non-commutative geometry by looking at geometrical spaces, and in this way, we now actually really have a geometric picture which really explains essentially why nature did choose the standard model by telling you that the space-time as we know it has an extension, which is finite extension, and this finite extension is really peculiar, and it has certain symmetries. And following actually either classification of finite geometries or by a different starting point where space-time is axiomatized to have finite volume, for example, then you really can derive actually the non-commutative space, which really tells you that it is the unique answer. So essentially, if you're really working in non-commutative geometry as formulated by Alan Kohn, then it tells you actually that the standard model is essentially the only explanation, the only model that would result at very low energies. And in this way, that's a starting point. And then in this case, one can really take this starting point and try to quantize the whole thing by building the geometry of space-time extended in a non-commutative way out of basic objects. In this case, what we have shown with Slava Mukhanov is that you really can rebuild geometry of space-time out of inverse maps from spheres, which are considered to be quantum geometry. So in this case, actually, one really can argue for such scenarios which was not addressed. So in this way, actually, even string theory has really no explanation now why standard model is the answer, because you have billions of possibilities to go down, and why one of them is a standard model is not really clear. So at least, there is an advantage here, and unfortunately, this has been completely ignored by the community. Nobody mentioned that. You see, the accusation is that you already know the answer, and because you know the answer, it means that you go. But it's not that simple, People have been trying to cook up an answer for a long time, and nobody managed to do it. And so in this non-commutative picture, you have explanation why the Higgs fields are there, why, for example, neutrinos have very small mass, and things like that. So there are really many successes on that front. Another point I would like also to say, to mention, is that, which was not addressed here, actually, because if you really read news from the particle physics community, there is a lot of somehow people are giving up, essentially. You see a lot of negativeness that, they say string theory failed, supersymmetry is not found, and things like that. But I think this is really the wrong message, because we know, for example, supersymmetry was really found by accident, I would say. It could have been missed, except for the people like Sergio here. They managed to find a consistent theory of supersymmetry. It's very compelling. But let's assume that nature did not choose supersymmetry, which is, it's a good possibility that nature is not supersymmetric. Does it mean actually that all this work is gone, and then we should give up? And the answer is no, actually, because first of all, when you work in a certain field, there are lessons that people learned. So many lessons were learned during this process. And second, people now have more freedom to explore other possibilities, and the other possibilities are there. Some possibilities they have more people working on, other models are less. But in the end, this actually somehow frees people to explore possibilities. And I'm sure actually that after some time, people will hit on something, and progress will be made. So I think actually, especially for the young people, there's no need for this gloom that everything is failing and, this doesn't work and, people attacking each other. I think it's now the picture is not settled. There are various possibilities. Each one is trying to push his own point of view. And I think in the end, something is going to come up. And, they are positive in all the approaches, I would say. And in the end, I think, probably a combination of all the positive aspects will be merged. For a time being, actually, that's what we have. And I think it's quite encouraging. I don't have this gloomy picture that even if supersymmetry is not found, and accelerators, especially since in non-commutative geometry we say the standard model is the only possibility up to really very high energies, and after that you can only get a Paty-Salam model. So actually, this we have been saying actually for 7-8 years, but people laugh because they say, okay, this is a negative picture. It's not necessarily negative, because if there is nothing, there's nothing. You take it and then you try to build on it. Okay, thank you.
doesn't fulfill our wishes. Are there comments from the panel on this? Otherwise, are there other comments from the audience? Sorry.
I completely agree with your remark. Combination of all positive aspects will emerge and be a kind of step forward. By the way, I have a question to Sergio too. I mean, years ago, people wanted to have starting from the landscape certain parkour such that the standard model results, but I have never heard of any results. People didn't.
It's too difficult.
There are many models which but it's difficult to make predictive model. I mean, you have to make predictions.
Because I was not so against the landscape, because for me, I mean, I'm not in this field, but for me that was the initial conditions.
I'd like to interject on that. There's a substantial body of work about the vacuum of string theory that agrees with the standard model. Now, first of all, you have to say it's a difficult job. There are aspects of that that enter into domains of mathematics that are not worked out. But in particular, the Oxford group has on the order of 100 models that agree with the low-energy structure of the standard model. People have been working very hard to make string theory match with what we know. That is to say, match the top-down with the bottom-up approaches to physics. And it's a difficult job, but work is going on, and there is success. Partial success. You maybe don't know exactly how to work out the aspects that rely upon knowledge of the metric on these internal spaces. That is one of the points that's difficult. So there are numerical techniques, and Simon Donaldson has contributed to that. So there's a whole activity going on. I mean, people tend to say nothing has come out about the matching between low energy physics and string theory, and it's just not true. But it is a difficult task.
You don't gain any understanding. There are hundreds. Suppose you found hundreds of models, right? What does it mean?
Well, the standard model is just a field theory, right? In the space of field theories, it's one model. So once you've got your model, you have a structure, and you can explore the consequences. Well, that's another type of question.
I remember when there were only two tiers, E8 and SO32, and then now we have with compactification we have more things. Okay, I don't know if there are other comments on this point that Ali raised, which is the connection. Okay, connection between quantum spacetime and other interactions, the standard model, basically.
My understanding is that this non-commutative geometry that Alan Kohn started with the standard model gave some mass relations which, as far as I understand, are incompatible with the renormalization procedure. So is this non-commutative geometry compatible with renormalization?
That was the original. But then it turned out that there is a modification of the standard model, and there is a scalar field that gives mass to the right-handed neutrino, and that actually made the mass of the Higgs compatible with the observed mass, and it really stabilized the coupling constant, because, you know, if you only have the standard model, you know that at 10 to the 11, 10 to the 12, the coupling constant of the Higgs field becomes negative. So with this scalar field, which is really part of the spectral picture, then everything is okay. So at that time, this was missed in the original analysis, and then it was, you know, later realized that it was not taken into account. So that actually was somehow a mistake on our part, I would say.
I think that Sergio was already referred to the original relation between the mass of the Higgs and the top, which was a classical relation. And now, no, now all the relations are based on the renormalization flow, and they are based on the unification of interactions at some point. And then there are what you said. Okay. There are, yeah, Professor Lukierski has some comments.
I would like to comment on the following question, because we did hear that one can, so to say, make a firm base out of quantum mechanics. But quantum mechanics is rather a kind of intermediary step. as far as the standard quantized twistor theory is a kind of intermediary step before really application of twistors to quantum gravity. And you described us today a first step, I mean the palatial twistors, I mean going outside of the quantum mechanical twistors, yeah? Okay, but what I mean that if you have a quantum mechanics depends in which background you discuss it. I mean, if you consider, for example, in electrodynamics, quantum mechanics, you have already the canonical relations are also changed because p's are not commuting. Okay, so what I'm saying that the presence of gravity implies, in some sense, the fact that you have a next scale, and this scale leads to, I would say, non-commutative structure. Because I think it's an old story from 90s. I think Doppler was discussing this thing in detail. That if you have a measurement, then if you want to measure the distances, then if you put too much energy, then you get a small black hole. And this black hole covers you, the possibility of measurement of arbitrarily small distances. So this is an argument against going with smooth space-time up to, so to say, zero, because before you are blocked. And effectively, so to say, if you translate the kind of new form of Heisenberg-Center relations which you get for space-time, you get non-commutativity of space-time. So I think in that sense, I think it is going far beyond, so to say, quantum mechanics, the presence of quantum theory with gravity. So this is my comment. So this is this next stage which we have to enter. I mean, this is above quantum mechanics, above quantum field theory in a standard form.
Yeah, the comments from the panel?
It's an elder argument. I mean, artified leader did it much earlier, and a number of people did it much earlier.
1809, as I think, also, I mean, there were some vague things earlier.
Bronstein.
Okay,
Bronstein, 36, I guess.
Yeah.
Unfortunately,
Yeah, well, Bronstein was taken by the Stalin police shortly afterwards, so he didn't have much chance of advertising his work.
Was that killed because of quantum gravity?
I don't think so, but we are not in that regime anymore. So at most we don't get a position. You want to say something?
I just have a brief comment on that last point, which is that that argument assumes that black holes and classical horizons make perfect sense at very short scales. And there might be options for theories of quantum gravity where black holes are only approximate or emergent notions. So perhaps there might still be ways around that argument.
Yes, but you don't measure it. It makes sense, but what Sir Roger was saying, that there is a problem of measurement, not of making sense. And there is an issue whether something that you cannot measure is there. It's like talking of the inside of a black hole. Sure, certainly there will be something inside of a black hole. It's a typical question that laymen ask you, no, what happens inside of a black hole? And usually the answer is that, who cares? we have no idea of testing it. So for what we are concerned is not there. And then if you have fallen into a black hole, then you are there. But from the outside, there is a... So the issue is not the existence of singularities, but it's the measurability. That's the...
So the operational measurement, I mean, makes the measurement up to the distance of Planck length, yeah? So because of this, then I think from the point of view, of an operational point of view, the non-computativity is just the kind of algebraic counterpart of this uncertainty relation which you get in measurement.
Okay, you want to say something?
I'm just a little worried about the measurement in the black hole. I mean, you could have an experiment, you could have a huge black hole, which you have lots of time to do experiments as you fall through, And just because people outside it can't measure anything inside doesn't invalidate the theory to apply inside the black hole. So somebody could fall in and do lots of measurements, and the space-time, as long as it hasn't blown up in some way, is perfectly consistent with the theory. I'm not quite sure what you were saying in that regard.
The statement is that you cannot measure too small a volume, because if you concentrate too much energy, then you develop an horizon. But so it's not a Planck length measurement. And Petru was saying that, of course, there are singularities, you can be arbitrarily close to it. But the point is that can you measure with arbitrary precision two very close by points? And there was an argument started with Bronstein about this issue. So it's, of course, the theory has points everywhere, but like if you have a classical phase space, you have something, but then if you do the Moyal product, for example, then you cannot measure things.
I appreciate that. I'm just a little worried about blaming the black hole.
No. Yes, of course. Yeah, sure. You can make a measurement, but this is inside of an infinitesimal black hole.
Sergio, what they worked out is a little bit more complicated, because in one direction, so to say, it's possible to undergo the Planck lengths, but in the other one, of course, then they are not. It's a kind of uncertain difference.
Yeah, it's like the uncertainty principle. No, you can measure with arbitrary precision a position if you give up any knowledge of momentum. You want to say something, Sergio? No? Okay. Okay.
I mean, this question of merit, it's just a similar point we were making before. I mean, people say you can't measure anything outside our particle horizon, you see. So philosophically, one might say, well, what's the point of talking about it if you can't see it? And it's in principle. Well, it's curious that in the cosmological scheme, which I'll talk about tomorrow, you can, because you can see beyond. So I guess it's a little word of caution, that's all it is. You might have a view that something is, in current theory, beyond measurement, but nevertheless has a role to play within a scheme which goes beyond that. And we have to be a little bit careful about saying something is non-measurable for some reason. I'm not saying you're saying that, but and I can certainly understand for little tiny Planck scale objects, the issue of measuring something might really be serious, because what you measure it with, and you've got these issues that you bring up about complementary variables and so on. Sure.
Okay. Sergio, please. You have a microphone.
Another subject which is closely connected to the subject we have been discussing is another kind of duality, which is the one coming from the conformal field theory anti-de Sitter correspondence of Joan Maldacena. That theory, that duality make a relation between holographically between gauge theories in 4 dimensions and theory of gravity in a higher dimension in anti-de Sitter space. So this is also something which match classical phenomena in one theory with quantum phenomena in another theory, and it is considered one of the main discoveries of the recent decades.
That's ADS-CFT you're talking about. Well, I worry about that again, because, I mean, it's something worth exploring, and that's fine. But what I'm worried about is what it has to say about the world we live in, because it's got a different number of dimensions, and you've got this big S5, which, why don't we see something to do with it? Because it's big. I mean, lots of issues here. And as an example of something to spend time on, because it's interesting and presents physical issues which you can explore, which you might have not in other circumstances, that's fine. But if you're saying this is a theory of the world we know, then it's not fine as far as I'm concerned, because it has very little to do with it. maybe indirectly it might, through theories which you understand the theories better, and so you can say something about the world we live in better. But I don't see it has much directly to say about the world we live in. Got the wrong number of spatial dimensions for a start.
Yeah, but positive mathematical results, I mean, you can ask, you can ask whatever you like, but the important point, I think, is provide models which are consistent.
I understand.
And provide ideas which are consistent. And these ideas, conformal field theory is one of them, I think. There are not many ideas which you can phrase, but certainly the relation between theory of gravity and strongly coupled gauge theories is a very deep relation, even if it works only in particular models which are not connected with our world.
No, I think you were saying the same thing.
Yeah.
It's fine to study these things.
Yes.
If they're not models of the world we know.
Well, if...
I would like to comment on this and again support Sergio's point of view a little bit, because I think there are 2 points, 2 sides to the ADS-CFT correspondence. You can say it's a proof of the concept of quantum gravity. We now know that, at least in that context of the arguably unrealistic 5-dimensional quantum gravity on entire de Sitter space, we know exactly how to define the theory by the dual conformal field theory. But there is also the other side, where people have been, over the past several decades now, applying gravity duality to understand the field theory side better. And that could be very useful for shedding light on very mundane, very interesting questions in field theory, including in condensed matter physics. So maybe quantum gravity will end up playing the role of the crucial tool that's missing in order to solve various strongly coupled field theories related to things even such as superconductivity that was mentioned earlier. So I wouldn't rule out ADS-CFT correspondence yet as a possible theory of things that have something to do with the real world. It could just come from surprising applications.
Yeah, I think you're saying that, I mean, as models to study, that's fine, and I have nothing against that. It's just that we have to distinguish those models which have a chance of being directly related to the physical world and those which we study to gain insights, and that's fine. Insights into this kind of how theories interrelate and general principles, and I'm happy with that.
With this, happy with that, I think it's a good sentence to end the round table, which was infinite radius round table. And I thank all the panelists and the audience. And okay, thank you very much.